Today we're going to talk a little bit about electromagnetic fault injection. We spent some time glitching the GigaDevice GD32F407. My name is Jonathan Andersson. I manage the advanced security research team at Trend Micro. We work a lot in conjunction with ZDI. We do a lot of hardware research helping to support the program. Today I have my colleague here, Thanos Kaliyanakis, and he's going to assist also with this presentation. So jumping in, here we have a picture of the part itself, and what you see there is the probe tip of the Pico EMP, and this is kind of a close-up view of how the glitching actually works. Thanos is going to kind of go through an introduction, give you a little background. He'll talk about how to get started in glitching, the attack we designed, and then I'll jump in and talk about actually executing the attack, how you can go about calibrating your system and optimizing it. We'll talk about some of the results and some mitigations and come to some conclusions. So I'm going to hand it over to Thanos here, and he's going to give you a little bit of intro and background.
Thank you, Jonathan, and welcome everyone. I want to start off quickly talking about some of the motivations we had going into this project, why we chose this particular part. Trend Micro ZDI operates several point-to-own events throughout the year. At the last automotive event, the Autel Maxi Charger was featured as one of the targets. Inside that device is where the GD32F407 device is. Why do we choose fault injection? We wanted to understand the experience our contestants were having with the part. It's locked, and we wanted to understand any difficulties they encountered firsthand. Specifically, why EM fault injection. We did not readily have access to any of the internal voltage regulation inside the part. Nothing was exposed, so we felt EM fault injection was the most likely to succeed for this part. So here we see a picture of two chip die. On the right is the ST Micro device, and on the left is the GigaDevice's device. These are software compatible devices. However, you can clearly see there's several differences. Where the ST Micro is single die device, the GD device is actually consists of the main die plus a flash chiplet. So the implementation is different, even though they're functionally similar. The reason I bring this up is because we found a bit of prior research on fault injection of the ST Micro part and nothing on the GD part. So we're hoping to leverage some of that in part of our experiments. Brief word about the readout protection levels. I'll only mention the RDP1 because that's the mode the part is in. Flash is accessible in flash boot mode, and when the flash is disabled when the debugger is attached. So there's some limitations there. Let's talk about the rig. On the right there is a picture of our particular rig. And the left is obviously the main components. Came in at about $600, not including the controller PC. And I'll go a little more in depth on those. So controller PC on the left and the target itself on the right. You may recognize this as an inexpensive desktop CNC machine that we leveraged for our XYZ platform. We removed the spindle and mounted the Pico EMP, which creates the EM pulses for to attack the target. Of note as well is the power supply. What's special about this one, it's programmable through software, but it also can measure the current draw of the target, both critical factors in this testing. Also of note is the managed USB hub. The special thing about this one is that each port can be power cycled independently. Very important when you're having any flakiness in any of your components, you can power cycle it and resume the testing. You don't abort the entire test run. Some purchase links for later reference on the main components. Bit about the 3D printed parts. Obviously the Pico EMP mount Like I said, it replaces where the spindle would go, and some handy platform mounts for the target PCB itself. And then we also leverage Thingiverse for some limit switch mounts that our machine didn't have. For our components, they'll be in the blog, posted in the blog soon. The chip shouter itself, some of you may be aware of it, but it's an open source project, hardware and software. Unfortunately, you can't just always purchase it complete, and you may end up having to do what we did, is put it together ourselves. We included the bombs here for some convenience, and we do have the PCBs are relatively easy to order and not expensive, but we do have a few spares if anybody's interested in getting one after the talk. As for the firmware for this Pico MP, we augmented it with an all-in-one command to speed up some of the sequencing that we do. And we utilize its PIO block for more deterministic timing and for triggering. And so these are some of the improvements that we made on that, and we'll try to post that to the original Git as well. So what do you do to get started in a project like this? Fortunately, it's some homework. You're going to be doing some reading, understanding the intricacies of the part, especially when it comes to security features. Prior research certainly is very helpful. The more you know, the easier it'll be for you to understand what the behavior of the part is, or at least characterize the behavior of the part. After you educate yourself, then you'll want to actually test that knowledge. And it's very important to look at edge cases, look at different modes, try everything that maybe not necessarily standard operation, just to see if there's any conditions that you can exploit later. Then you'll have to decide which dimensions to control. By far the most important element will be the trigger. And we'll talk in more detail later about which aspects are the important ones. And then the rest of the parameters are fairly typical for this EM type setup, EMP fault injection setup. And then what do we collect after we do the controlling? Obviously, everything you've controlled, you're going to want to also log and collect, as well as any information you can gather from the target. Current draw, any IO or clock out measurements you can take. If you have access to a debugger in that mode that it's in, any information from that is helpful. Console output is helpful. So those are the type of things you want to collect. Also, don't neglect to instrument your glitch loop, the code that you're using to run all this on. It's important to keep your glitch rate up, and we'll talk about that later. But having good way to monitor your performance in the glitch loop is important so you can optimize it. And finally, use a scope and other lab equipment as much as possible to validate everything. You're going to have some new hardware, new software running together. It's going to help a lot. And don't just take it off, just leave it on if you can, because you'll want to be able to make sure that it's still operating to form as you progress through your testing. Very quick word on coding and ops. Most of these are just best practice type recommendations for good logging and tracking. You'll be dealing with a lot of data and a lot of test runs with subtle differences, and you're looking for a needle in a haystack. So if you're not keeping good track of these things, you may miss some important information that could help you, and it'll extend the time you're testing. So let's talk about the attack. From prior research, we suspected that the GigaDevice's device was susceptible to being attacked in bootloader mode because the ST micro showed that it could be. So we extracted the bootloader code from the device. We reversed it in Ghidra, and then we verified that the command set in the bootloader matched the ST micro. So the same read memory command existed and operated in the same way. So the attack was to boot into bootloader, issue the read memory command, perform our fault injection, and then wait for a NAC or an ACK, in this case a hex 79, to affirm that we could access the firmware. What this looks like in the code was, over here on the right, the read memory command would be transmitted to the target. It would be decoded and call the read memory command function. Just above the blue arrow is where the lock bits are stored in the device, and then the conditional check to see if the device is locked. And if the glitch, which would be aligned where the blue arrow is, was successful, it would fall through to the ACK, the hex 79 message, and then we'd have access to the flash. So that's what it looked like in code. What this appears like in time, starting from the yellow up in the left, the read memory command being transmitted to the target. The Pico MP here is monitoring the signal and will trigger at that last edge, and then initiate its programmable delay, which will vary from glitch to glitch. And then at some program delay, the glitch would happen here in green. And then the conclusion of the cycle would be the response from the target in red, which would be, in this case, it's a NAC. But what this clearly defines here is the ultimate window of where the RDP check would be happening. So the blue arrow there indicates the maximum range of the RDP check. So let me hand it back over to Jonathan. He'll continue with the process that we used.
Thanks. So we talked a little bit about the rig, how to get started, and what the attack is like. So let's talk about actually implementing the attack, how to begin, how to get your rig basically functioning, and then we'll move on to some optimizations and results. So here in the bottom left, you can see a picture of our probe. We kind of constructed the probe following the instructions that are in the open source repo for Pico EMP, so you can follow those as well. You can see we sharpened the tip as they recommend as optional. It seemed to work for us. We also added this red wire here. We just hot glued it on. And the reason we did this, of course, Thanos mentioned that you might be building your own Pico EMP. You might be soldering it yourself. And you don't want to spend a lot of time wasted if the Pico EMP isn't working. So this is an easy way. If you hook this wire to your scope, you can validate that you're actually getting glitches when you expect to be. And we ran it that way for a while until we got confidence in our system. Then in order to calibrate and continue, kind of get your system set up, you're going to want to find sensitive spots on the chip. And this helps you learn which areas can be most susceptible to useful glitches. And the way you're going to do that, scan in a spiral, and you're going to want to hit the chip as hard as you can using strong glitches. And kind of what we define as strong glitches is where you have a minimum distance between the pulse probe tip and the device itself. As well, you should have the maximum pulse power, which is the longest time that the EMP switch is open, so the capacitor bank can dump all of its energy into the probe. And then it's also important to use, and this is less obvious, but important to use the minimum VCC that you can with the chip. And in order to do that, you're going to need to remove brownout protections from your target chip. And the way we did this on the GigaDevices is there's a single pin which allows you to do so. So we lifted that pin and then brownout protections were removed. So this puts the chip in the most vulnerable state, the most pliable state, and hits it as hard as you can. And then, as mentioned, you're going to go in a spiral, glitch many times at each point and collect data. And what you're looking for as you log all of this data is any response from the chip at all. And then you log all this data to create your map. Now, one of the fastest ways to see if you're having an influence on the chip is to measure its current draw. And so it's recommended here. So if you see the current normally operates at around 65 milliamps, if you glitch the part and see that it drops to 2 milliamps, 1 milliamp, 0 milliamps, you know your glitch had an influence and you know that's a sensitive spot, so log it and keep going. Other things you can look for, if the part resets, you can also connect the debugger and log the program counter. You can look for like clock output signals. If it has a clock out and the clock out becomes malformed or stops operating completely, that's a good sign. If you have external memory buses that are present and they stop functioning, you can also consider that influence. So scan the chip, map all this influence. Here you can see an example of one of our early on scans, and this is when we found the first sensitive area here in red. So let's talk about why spirals. Well, after we did some work, we kind of came to these observations. We haven't seen really other people talk about it, but you can see here on the left that is a picture of the dye in the chip, which has been chemically exposed. And so that's, again, a smaller version of the picture that Thanos showed earlier. Then in the middle here, you can see an example picture of what it would look like if we took away all the plastic from the part. And what you're seeing there is called the lead frame. And that's in a QFP, in a quad flat pack device part. The die is mounted in the center. You have bond wires which connect to each one of these leads and then extends out to the pins on the edges. Then what you see on the far right here is the result of one of our scans. And there's some things we started to observe once we started scanning. You can see that these sensitive regions pictured here kind of have alignment with the edge of the leads in the lead frame. And it kind of makes sense, you know, with electromagnetic glitching, you're kind of inducing currents in the leads, which kind of align with the edges of the lead frame. So these were interesting observations. A couple of other things to note here are the colors of the dots matter. It's kind of the palette of a flame, meaning the darker colors are low current draw. As it goes to orange and red, it's more current, and white and bright yellow is even more current. So you can see there's a unique region here in the upper right where the current draw or the glitches typically cause a brownout. In other areas, it's different. It just so happens that there's some oscillator in pins here, which probably cause the part to just crash. So how do we further calibrate and move forward with our attack? So in the initial phase, we're scanning, we're looking for any sensitive spot. And like I said, we're punching the chip really hard, we're causing it to crash. But if you cause the chip to crash, you're not going to get any continuation, so your glitch is not really going to be useful. So the second part of calibration is, you know, seeking to one particular sensitive spot and then kind of dialing it back. You want to reduce the glitching power so that you do get continuation. And the way to do that is to, you know, decrease the pulse power and increase the voltage and kind of see what working ranges that you can come up with. And those will be the ranges that you use in your brute force attack. It's also useful to find a minimum voltage, the minimum VCC. So here we saw that the chip can operate barely down to 1.5 volts with brownout protections removed. And at that voltage, almost any time we glitch it, 98% of the time when we glitch it, the debugger is unable to connect at that point and read the PC. So the part is definitely locking up, or at least portions of it are. Also at that voltage, about half the time, the current drops to zero, browns out. Raising it even 1/10 of a volt, those numbers drop down to 30%, and another 100th of a volt above that, the chip starts to mostly have some influence, but it doesn't always brown out, which is useful. So this is kind of a boundary where the chip is very susceptible and is a good place to glitch. And here I call it a balance mix, but it's kind of like the borderline between an operation and you know, glitch always causing a failure. And I want to point out too that each sensitive area might have a different calibration between pulse power and VCC. So if you move to a new area, you might find it useful to recalibrate. Let's also talk about other ways of characterizing the level of glitch influence. If you connect the debugger after the glitch, you can read the PC and kind of learn something from that, right? If the PC is unreadable, as we mentioned, you might consider that extreme influence. The part's locked. If the glitch is in an ISR, maybe it jumps to a hard fault or a bus fault and just loops there and and you can see that as well. That's more of like a medium level influence. Or maybe the PC is still in the expected code loop. In our case, we were attacking the bootloader, so it was in a serial receive loop. So if it's still in that loop, maybe it only jumped 1 and 2 instructions, or maybe it jumped no instructions. So that's kind of a low or an optimum influence in some ways. By reading the PC, you can also see other useful things. Did it jump to RAM? Did it jump to other memory addresses that are useful? So it's also useful for other reasons. So once you have kind of calibration, you've picked a sensitive spot, you're progressing in your attack, let's talk about things you can do to optimize it and have better results faster. As Thanos mentioned, a stable trigger is really important. You're going to need hard timing between your trigger, your delay, and your glitch, and it needs to be on the nanosecond scale, in the order of clock cycles. If you don't have this, you're not likely to be successful. Don't try to read from an I/O pin, then issue a trigger, then issue a glitch over USB or something. It's not likely to be successful. And for certain attacks, glitching sooner in the boot process is definitely better. Once you get multitasking going, multiprocessing, you're going to have a lot of complexity there. It's going to be really hard to kind of understand what's going on and place your glitch. Another thing that can be really useful is ARM fault status registers. If you do have a fault, there's registers in ARM which will record the location of the faulting program counter. So if you use a strong glitch and you get a fault, you can then connect the debugger and find out exactly where that glitch was in time, which is very useful. It helps calibrate your glitch point to your exact code that was running at the time. And this can help to reduce the delay window down from the large one that kind of Thanos was describing, down to one which is much, much smaller, and it's a huge optimization. I will point out that there's also a blog by Memfault. He'll explain all about it. And if you can't read these registers, again, you're kind of reduced to a much wider brute force range. And then we're still talking glitch rate optimization is key. We talked about correlated parameters, correlated dimensions with voltage and VCC and your Z distance. But what might not be obvious is you don't need to vary all of them in your brute force loop. You can kind of fix at one VCC and then vary the pulse power and also kind of leave Z where it is. We didn't really find it useful to vary Z. And as mentioned also, classify glitch results as fast as you can. If in our case we're using a attack to the bootloader, which is over a serial protocol, so we issue a command and wait for a response, right? Now, if we issue a command, perform our glitch, and we can see that there's zero current draw from the part, why would we wait another second or two to see that the protocol doesn't respond? At the time the current drops to zero, we already know the part's incapable of responding, so at that point you should terminate the glitch loop and go to the next glitch. This is also a big optimization. We also found that minimizing the EMP charging time was another big one. Out of the box, the open source code, the Pico EMP can take like 1.5 to 2 seconds to charge. So I did a little fuzzing to figure out the optimum charge rate, the PWM charge frequency and duty cycle that worked well. So we kind of found a couple parameter sets that we were using here to take the time down from like 1.5, 2 seconds to 1/3 of a second or 1/4 of a second. So another huge optimization. Definitely try to parallelize things. Move while you're charging. It's kind of obvious. And again, Thanos already mentioned, keep track of your timing of your code loops in your logs. You can see if they start increasing. If you add one small thing in code, sometimes it's not obvious that it's going to add a lot of time to your glitch loop. So with analysis, in the beginning, we were looking at a lot of text-based logs and trying to make decisions. And that became very challenging over time. And eventually we broke down and like, okay, let's start graphing and analyzing it from different perspectives. And it's a must. We'll show you some analysis in a couple of slides, and you'll kind of see that. Also, when you're making decisions, consider if your observation is unambiguous, and don't be too rigid in how you're doing your analysis, and especially try to frame it in the context of the SOC subsystems that are available on your chip. For instance, if you have a reset, is that because you triggered a brownout circuit? Is it because you jumped to an ISR and then a watchdog triggered? Is it because there's a clock monitoring circuit and you glitched a clock line and that caused the reset? So the same thing can have actually different causes. And we definitely use an unlock development board, not only to get firmware, but to compare sensitive regions and things like that. So that was also useful. So what if you get stuck or you get lost? try a new sensitive region, jump from the one you've been working on to a new one, recalibrate, rescan. Definitely also do this if you see no influence or if things change unexpectedly, if you change the probe tip or change the EMP pulsar itself, a good time to recalibrate. And if you're completely stuck, it's kind of hard to give advice on a problem I don't have a lot of details about, but in general, controlling variables precisely is really important in EMFI, including timing, target voltage, and things of this nature. So make sure you're controlling them accurately and measuring accurately. So let's talk about the results. So there's a lot going on here, but from the top of the slide is the file name of our log. There's about 200,000 glitches in this particular run. We were running at, looks like 1.62 volts. There's some delay and pulse power counters there, D and P, and those are in increments of 8 nanoseconds. So looking more closely at the graphs, each square in the center, you have in the blue the main die and the flash chiplet, and then around the edge you have the part pins, and the pin 1 being in the top right. So some things of note, starting at the bottom right, you can see, there were quite a bit of brownouts, but we also had modified code flows. So we had a mix of, part crashes and continuations. So we can tell that we're kind of operating in a sweet spot. Additionally, you can see we had dead beefs, and dead beef is when we connected the debugger and couldn't read the PC at all. We had some times where we jumped to SRAM. We had times when we jumped to other ISRs. Again, as mentioned, modified code flows. So we were still running, but we were not in the original serial receive loop as we expected. And then probably most importantly, we had some actual acts. So here's 48 that we had over this particular run. And they weren't all necessarily continuation, meaning it might have returned an act but crashed sometimes after, or had memory corruption after and crashed, something like this. But that's at least 48 that passed the initial check. So, 10 million glitches later, we were successful, right? From the beginning to this point, we spent about 4 months, but we had never done it before. We built it from scratch. We programmed it from scratch. And we were at least happy to get to this point. Unfortunately, after we got continuation, further, when it tried to read the flash, we had some hard faults. And this is described in the data sheet. It wasn't unexpected, but we felt like we wanted to check this. So the flash is disabled, even with the debugger disconnected in bootloader mode. So what do we do next? Well, from our experimentation, we had observed that the SRAM contents of this part are persistent after a hardware reset. So if you do a pin reset, the SRAM stays. So we thought, all right, well, that's at least a starting point. We had also noticed that we had logged some jumps to PC SRAM, as we saw before. So let's combine those two, right? So for the second attack, we decided to inject a NOP slide into SRAM, followed by a dump routine, and then reset and glitch early during reboot, as we kind of talked about, and see what happens. And I will point out that there are several important regions to save, not only the flash region, and this part has a battery-backed SRAM region, which is locked, as well as some PC RTC registers, which have some user data you could store, and we wanted to make sure we captured those in case there was key material or something there. So this is a little bit of a nod to prior research. Brute forcing is a big waiting game. It can feel like this, but hopefully some of the things we mentioned in this talk can help you minimize this part. And I will say, from the beginning to the first attack, again, took the bulk of the time. And then about 2 days later after the pivot, we were actually successful in extracting the flash. And so here you can see, this is the log line. We're operating at 2 volts. These are the coordinates of the glitch in XYZ. We're using a delay of 7.8 milliseconds, and the EMP switch was open for 288 nanoseconds. And we were able to get it to jump to our NOP slide, slide down to our firmware extraction routine, and extract the firmware. So we were happy to get to this point after such a long effort. Also, a bonus to everyone, during this time we found a simple bypass. So while we were developing the code for firmware extraction in SRAM, we kept copying it to SRAM, changing it, debugging it, and doing this. So at one point when we copied the SRAM, we set the PC to the SRAM as well. We disconnected the debugger, and we found out that the part started running free and then spit the flash out. So nice bonus for that. And clearly it's something that shouldn't happen, but kind of going back to the beginning, it's important to try all your edge cases and exercise everything. Don't believe what the datasheet says for sure. So let's talk about some mitigation. So GigaDevices probably can patch this in a follow-on tape out, at least the bypass. Maybe they can change a few things without a lot of redesign and cost and expense. It's possible. But I think applying additional hardware to do EMFI mitigations is not so easy and it seems unlikely. So even if they do patch the bypass, probably still have a route in through EMFI. Another interesting thing to note is at one point when we were researching, we decided to update our J-Link. We applied new firmware, and then the next thing you know, we saw this dialog in the bottom, and basically the dialog is saying, you're not allowed to connect to the part at all anymore. You must erase the part, and as a result of unerasing it, also unlocks it, and then you can use a blank part. So we were like, hey, this used to work before, what happened? We rolled the application firmware back while leaving the J-Link firmware in the latest version. And once we rolled the application firmware back, this dialog went away and we were able to use the part. So in effect, this is a pseudo mitigation. Is this something that Seger did on purpose in terms of security? Did they work with GigaDevices? We don't know the answer to any of that. But long story short, it does block research into lock parts, and it's not cool, and it's obfuscation. So if you're going to do this kind of research, either don't use the latest version of J-Link or, just don't. So, overall, what have we learned? Fault injections, brute force, it can take a lot of time, but hopefully we've given you guys a lot of tips and things that can help reduce the time. As we talked about, the PZ, VCC correlation, the charge rate optimization. We also optimize commands inside the Pico EMP. And certainly the ARM fault status registers as well are very useful for reducing your overall brute force kind of space and helping you get results faster. So prepare yourself for brute force. Don't get discouraged. This was our first time, but we got it to work. So in the end, again, we have a simple bypass. Even if it's patched, you probably still have a way in through glitching. And we feel like with EMFI, there's kind of a basic process you can use in terms of calibration, scanning for sensitive areas, do some tuning to optimize, make sure you're analyzing your data as you're going, graph it from multiple angles, make sure you're documenting your data, keep tabs on your glitch rate, and you can also be successful. So I don't know if there's any questions.